Good morning, everybody. Buongiorno. So, it's a real pleasure to be here this morning. And it's really nice to see that, one of the key topics of this conference is going to be IoT. So, we're here today to talk about Android things. And so, I'm a developer advocate at Google, and my job is to talk about IoT and the Google Assistant and other, different kinds of products at Google. So, we're here today to talk about these things and give you some more information about what we're working on and some of the things we're working on for the future. And also, we're here not just to talk to you all about what we're doing, but also to get feedback from you. So one of the things I really like about going to events like this is that we get to talk to developers just like you, find out the kind of things you're working on, and then feed that information back to the product teams. So I work with the engineers quite often who design a lot of these things. We meet with them every week or every day or whatever. And so I'm your gateway to get things back to them. So make a point of coming to talk to us at this event. So I've got one of my colleagues, Jonathan, here as well. He's one of the engineers. So Jonathan wrote some of the samples that you'll be using for Android things as well. So between me and him, come and talk to us, and we really want to hear what you have to say because that's really good information for us. So with that in mind, let's talk about Android things and what that means for the Android ecosystem. So I assume because you're here, you're all familiar with Android and that you're a big Android developer. So what we're announcing with Android things is we're extending the Android ecosystem to support a range of new devices. So we have an existing family of Android, which is Android on mobile, Android Wear, Android TV, and Android Auto. And now we have Android things. And the nice thing is that we're taking everything you know about Android and we're extending it to IoT. So as a developer, you've invested a lot of your time and your energy and years of development effort building libraries and code. You can take advantage of all that because Android things is based on Android. So you get to take advantage of all the things that you have and deploy them for building Internet of Things devices. And nextly, security is hard. As we've seen with devices, there's a lot of people trying to attack infrastructure and software and so forth, and it's really important to have very secure IoT devices. The consumers who buy products need secure devices so that they can be certain that the device is going to perform correctly and that it's not going to cause problems for them. And as a developer, you need to be aware of security and take care of that. Now, you could build your own everything. You could build your own kernels and distribution and software to put on your devices, but then you have to become a security expert and keep an eye on patches and security information. Instead, we take care of these things for you. And so we provide you a secure platform that's updated, and you can rely on that to provide your security for what you're working on. And then finally, we provide scaling to production. So it's one thing to take something like a Raspberry Pi and hook some wires and lights up to it, but it's very difficult to sell that because the developer kits are expensive and you can't sell a device for $5 if there's a lot of expensive components that go into it. And so we have a roadmap to production, which we're going to talk about later on, where you can take your device, prototype it, and then when you're ready, you can build custom devices very easily that scale, that can be made in large quantities, but they're also cheap to manufacture in small quantities if you want to. So that's what Android things is all about. And it allows you to take advantage of Android's best-in-class multimedia, connectivity, and all the rich user interface layouts and toolkits that you're familiar with to simplify and accelerate the development of your IoT devices. Up until now, IoT development has been hard and complicated and painful, and we're trying to make that a lot easier now. So, what can we use Android things for? Well, Android things, the devices are very powerful computers. They have processors in them that are very similar to what's in your phone. So they're ideal for doing vision processing and audio processing. They're great for building devices that are intelligent, that work on the edge, that need to securely connect to cloud services. And so good examples are devices that are sort of aggregating multiple sensors, doing a lot of processing, and they're doing it locally, and then you can upload things to the cloud if you want. So it really gives you choices as to where you do it. You don't have to upload everything to the cloud. You can do it all locally. But you as a developer get to choose these things, and that's one of the really cool things about Android things is it enables this kind of functionality. So with that in mind, it's a little bit of an intro. Now let's talk about what it means to go from prototype to production with Android things and how we simplify and accelerate the development of IoT products. Firstly, you develop with the power of Android, which we mentioned at the start. So everything that you know, such as Android Studio, the Android SDK, the Android NDK, all of those tools use them exactly the same way. In Android Studio, you go to a new project just like you do for a phone, and you create an activity, and you put code in there, and then you run it, and it runs on your device. So it's the same workflow that you're very familiar with. And you can take advantage of your code base that you've developed already, any third-party libraries that you're using, and the developer ecosystems that have built around those things. Next, you get to take advantage of all the great services that Google provides as an add-on. So for example, we have Google Play services on the device. So many of the APIs that you use from Google Play services, they're available on the device as well. And so you don't have to worry about re-implementing something that Google Play services already provides. Whatever you used on the phone, you can use on an IoT device as well. Furthermore, you have things like Firebase and the ability to integrate with the Google Cloud Platform too. So there's a lot of really cool things here. And actually, one of my favorite examples is just recently we did a blog post where we announced a new sample that we produced which showed how to use TensorFlow on an Android things device. So you could have a video camera and you could point it at pictures of animals and it would classify them for you based on a training algorithm. So it's really neat because it just takes photos and it tells you what kind of dog you're pointing the camera at, which is pretty neat with the kind of things that you can do locally on a device that's in your hand that you could sell and make an IoT product out of. So one of the really important things about Android things is that the system images that power the devices are managed by Google. So we build them, we sign them, and we push them out to devices via the IoT Developer Console. And so we manage the Android framework implementation, and we manage the hardware libraries and the Linux kernel files. So we take care of the security updates and things like that. And this is critical because what it means is that if the manufacturer of a device that's powered by Android things, if they disappear or stop updating their devices or become uninterested in their product anymore, Google still has the ability to push updates to the device to keep it secure so that it won't be a problem later on if a vulnerability is discovered. And so the developer of the device, all they need to worry about is making their app, and they worry about any configuration files that configure the device and make it work. And so the device is split into two parts, the Google updated portion and the developer updated portion with their specific app. And the app is where you build the functionality for the IoT device, such as blinking lights or controlling some switches or whatever you're trying to do. So with these updates, the updates are protected from corrupted image downloads and hacking and so forth, because the images, we check the signatures on them, we verify them to make sure that they've been not tampered with, and then they're installed onto the device using verified boot. Now, what we do when we do an update is we use the Android A/B updating mechanism. So an update comes in, and the OEM gets to decide when it gets to be installed on the device a little bit. Then the update is installed on the device, and if for any reason that the update fails, or if it fails to boot after the device restarts, it automatically falls back to the previous image. And so this is nice because you can roll out updates, but if anything goes wrong for any reason, the device will be rolled back to a known state that's safe, that allows the device to keep running so that you could issue a second update if you found a bug with it. So the update mechanism is designed to be very robust, and it's based on the same update mechanism that we use on Android phones right now. One of the most important features of Android things is this concept that we call a system on module, or a SOM. And what we've done is we've worked with various chip designers. So here you can see a board from NXP, and there's an Intel Edison board there. And we've worked with the chip designers to make these little SOMs, which are small little boards that contain CPU, memory, networking like Wi-Fi and so forth, and it's all integrated on a very small board. There's no external I/O. It's designed to be a very small reusable module. And we build software like kernels and libraries that fit up against that SOM. And you can customize anything outside of the SOM. Now it's nice because the SOMs are very tightly integrated, and there's something that's difficult for your average hacker to be able to solder a board like this because the packaging is quite tight. But you have the ability to create your own baseboards that plug into these things, and you can customize the kind of connectivity that it has with the outside world. So the nice thing is you can buy these very cheap SOMs, and you can build your own custom boards very cheaply as well. And because the baseboards use just sort of regular electronics with a much wider pitch, it's possible for you to make those boards pretty cheaply as well. There are many hardware companies around the world that will make these baseboards for you at very affordable prices. So what we're doing is we're democratizing hardware development here, in that you don't need to have a factory and millions of dollars of equipment to make IoT devices. You can make a small design, you can then work with a design house, and they'll make this board for you in small, large quantities at reasonably good prices, and you can have them manufactured and then sell them to people. And so, as part of these boards, we have what's called a BSP, or a board support package. The board support package is the software provided by Google that is the kernel and libraries that interface with the SOM. We provide all that for you. We handle the porting of anything. So we provide a general API, which we'll show you in a minute, that controls these devices, but it's generic. So if you write software once, it then runs on many different platforms without having to rewrite all your code again. And one of the problems with old IoT development was that you would have to work out how that particular Linux kernel exposed the GPIO pins, and then you'd have to work out how to enable them. It was very fiddly. We've made that a lot easier with this new SOM and BSP architecture, which makes things really easy. And actually, I have a talk at Google I/O coming up in a couple months, where me and Dave Smith are going to talk about how we went about making our own boards. And Dave taught me how to solder with a microscope and all this kind of stuff to actually make these boards ourselves. So it's really cool. So definitely check that out. So with that in mind, let's talk about how, let me just clear this. With that in mind, let's talk about some details about how Android Things is actually implemented. So this is your typical Android architecture diagram. So traditionally, it's always had a Linux kernel with a variety of drivers present. There's a bunch of libraries above it for OpenGL, SSL, things like that. And then we have the Android application framework that runs on top of that. That provides a variety of services that allows your apps to do things like controlling the Wi-Fi and getting location information, moving windows, and so forth. And then at the very top, you have the applications themselves that run on a phone. So you've got the launcher, you've got the notification shade, and things like that. So this is how a traditional Android phone is architected. With Android Things, what we've done is we've taken away all of the things that make it a phone, and now we make it a generic IoT device that's much more reusable. So you can see that we've gotten rid of notifications and the ability to make phone calls. It's not like you're going to hold a Raspberry Pi up to your ear and make a call to someone. And then we've removed things like wallpapers and soft keyboards and stuff like that. So these are things that were not needed because they're from a phone. And the nice thing is that we have all of the rest of these libraries that come from Android that are there to help you make your IoT apps amazing. And we have things like the UI toolkit and everything else. So there's a lot of cool functionality that we've kept, and we've removed the things that are not necessary, which allows us to put it on a very small device and not use the same resources that it would on a phone. So one of the cool things about Android Things is that displays are now optional. On a phone, you always had a display. Now you have a device like a controller that might not have a screen at all, but you can have a screen if you wish. And so you can have whatever you want for your particular application. So if you do have a device with a screen, then you can present your application on that screen with an activity, just like you would on an Android phone. And one of the cool things about Android Things is if you have one of the hardware devices, like a Raspberry Pi, you can just take your regular Android app, ADB install it onto the device, and it just kind of works. Plug your keyboard and a mouse in, and you're good to go. So the device kind of runs in a kiosk mode because there's no launcher or anything. Your app runs full screen all the time, and it's run at boot. Now, you don't have to have a display. You can decide to leave one out. What you do is you still create an activity. So on Android Things, you always must create one activity that is started when the device boots, and it goes through the regular Android lifecycle like it does on a phone. The difference is that your activity is never going to get killed like on a phone. So all the methods for the lifecycle are there, but you're not going to go through it at the same way that you will on a phone. But what happens is that if a keyboard is attached to your Android Things device and someone types on the keyboard, those key events will be sent to your activity just like they are on a phone. So you get all the benefits of the regular Android phone ecosystem, but it's in an activity that might not necessarily have a display anymore. Now, if you do have a display, you can use the regular Android layout and user interface toolkits to create your layouts for your devices. So that's kind of nice. You get to leverage all of that. So with the display being optional, you're going to ask, well, what happens if there's a pop-up dialog box that asks the user a question? So it might ask for authentication, or a system notification might pop up. So the way it works is that you can't obviously ask the user for authentication on a device that has no screen. And if you have like runtime permissions, for example, Android Things automatically returns true for permission checks for any kind of permission APIs that you might be asking for. And any permissions are granted at install time as well. So we don't ask those kind of things anymore because it doesn't make sense for a device like this. This is not a phone where you're installing hundreds of apps onto it. It's a dedicated device that happens to allow you as a developer to install one app onto it that is sort of baked into the device. So that's how Android Things works. And with the lack of a screen, you now need to start thinking about, well, how am I going to control such a device? So you don't have a touch screen anymore. You could if you want, but you might not have one. How else are you going to control it? So it might be a device, it might be a toaster that has a dial that you put it in when the bread goes in. Or you might use speech recognition, or you might have a game controller connected, or you might have a USB keyboard, you might have an accelerometer sensor. These are all examples of things that you could use to control it. And so the Android SDK already provides support for this. Some of you might not know this, but you can actually just plug a keyboard or a mouse into a phone, and it just works. Android's had support for these things for a long time. So now that we've gone through what's possible, now let's sort of show some examples of how you can go about quickly getting some code running on an Android Things device. The way you do it is you need to start off by including our support library. So the support library is built into the devices with a shared library. And then we have an SDK that's hosted on JCenter. So there are three things that you have to do. The first thing is in your build.gradle for the application, you include a provided that includes the support library followed by the version number. And that then brings in the dependencies when you build the project. The next thing you do is in your Android manifest.xml, which is just like on Android phones, you include a user's library, so that tells it to give it access to the shared library on the device. And then finally, you add an IoT launcher to the list of intents for the activity. And this tells the Android Things device that that's the activity that we want to start when the device boots. So when the device comes up, that activity gets started straight away. So that's pretty much the basics of the little things you need to do to the APK to make it so that it works on the device. So now we're ready to build some apps. So as I said, we support all the regular Android APIs, but what we also support are extensions to the Android framework that complement it to provide new APIs for performing I/O. Because when you're building an IoT device, interacting with the outside world is very important. So you need to talk to buttons and switches and lights and thermostats and things like that. We need to be able to interact with these things. So we support a variety of different interfaces in software out of the box with an abstraction to make things easy. For example, we have GPIO. So GPIO is general purpose I/O. And if you've made little devices before, it's things like buttons and switches, LEDs. Those are controlled by binary 1 or 0 valued GPIO pins. Next, we have pulse width modulation. So PWM is used to generate waveforms, and that's useful when you want to control a servo, like a robot arm, or some speakers, or make an LED blink, or have a certain brightness. We support I2C devices. There's a whole bunch of really cool devices that you can buy now that are like little, they're boards that have a bunch of functionality embedded into them. So there are things like temperature sensors and little display controllers and things like that. And you talk to them with a bus called I2C. Our hardware supports it, but we also provide software to abstract away all the messy details of talking to an I2C device. Same thing for SPI. It's a high-performance serial bus used for devices that need a bit more bandwidth. And then finally, we have UART support for devices that use legacy serial ports like GPSs and printers and things like that. So you can integrate with a wide variety of devices using our API. So here is a quick example that shows how to go about doing it. So with a couple lines of Java code, you have the ability to open up a GPIO device, wait for an event, and then do something about it. So you can see here that we start off by creating a peripheral manager service. We then say open GPIO. We pass in the name of the pin that we want. Then we set the triggering type. So this is really cool because instead of polling on the device, you can actually say, I want you to call me when an event happens. So in this case, we're saying edge falling. So that says when the waveform goes from 1 to 0, that's an event we're interested in. That could be a door switch or something like that. We then execute a callback here. So this is very familiar Java code to most of you if you've done UI programming. We have a method called onGPIOEdge, and that is called when the GPIO pin changed. So that's it. If you were writing raw Linux code to do this, you'd have to open something in the proc or the devfs file system. You'd have to mess around with the things, write values everywhere. We handle all that for you, and we do it in a secure way as well to help protect the device and make sure that there's less security vulnerabilities. And a similar kind of API is used for all of the different I/O interfaces that I just talked about. So there are many different types of devices that we support. And so you can support them directly using the code that we just did. But one thing we support now that's really cool is this concept called user space device drivers. So these are not traditional kernel drivers like you would normally work with, but these are sort of code that runs within your Android app that is used to provide further processing for a device. So for example, what you can do is you can actually create your own driver that plugs into the Android framework that can inject events into Android so that other applications running on the device can see it. So as an example, in terms of input, you could have it so that a button presses, it detects the GPIO edge falling, and then it generates a key down event. And the key down event is then sent into the framework, and then you could have a UI running on the screen, and it would press the OK button for you or something like that. But it's all done with regular Android framework calls. You also have the ability to plug in sensors. So Android has a sensor API that a developer can use to discover all the devices available. You can create your own virtual devices, or you can take some data from an accelerometer that you've read over an I2C bus. You can inject that into the sensor manager, and then it's available to any other code you've written that you may have used from a mobile phone or something like that. And the sensor manager interface is really cool because if no one's listening for the events, it can stop the sensor and it can re-enable it when someone's interested in those events. And the other thing you can do is you can take a GPS device, and so you can take a GPS module over serial, and rather than just processing those coordinates directly in your app, you have the ability to feed them into the Android framework, and then you can combine them with a fuse location provider, which then gives further improved accuracy for the positioning that you're doing. So all the nice things you get from Android are available for your sensors as well using the user driver framework. So how do we do this? So here's another example of where we're going to take a button press from a GPIO pin, and we're going to map it into key codes. So all we do is we create an input driver object, we use the builder method on it there, and we tell it we're dealing with a button. We then give it some names, you then register it. We then take that callback we wrote before, and we extend it by creating a key down or a key up, depending on what state the button was in. And then we emit the key event into the framework. And now any other code that's listening for on key down or on key up method calls will get called when this GPIO pin moves. So it's really nice because we've integrated all these external devices and made them first-class citizens in the Android framework. The next thing is that we now provide a peripheral driver library. So I mentioned before that there are many of these little devices you can buy, like little LCD screens, little touch panels. They'll have I2C buses and data sheets and things like that that you might not necessarily want to read. So engineers like Jonathan and other people on my team, they've gone and read all the data sheets for these things and implemented a variety of drivers for these things so that you don't even have to worry about talking to the I2C bus. You can just you can just create an object that implements a certain interface, and then you can just do set text methods, and it writes the strings necessary over I2C or whatever's necessary to make it work. And so these driver artifacts are hosted on JCenter, and so you can use them really easily from a build.gradle file, and they're also open source and available on GitHub as well. And if you're interested, if you've got a particular device that's not supported, either come and talk to us, or you can suggest it on our G+ community, and we could write a driver for it for you. And so here's an example of a driver that we wrote that abstracts all of that previous code away for mapping GPIO pins to button presses. So you can see here, we have a button input driver, we pass in the pin name, the direction, and the key code space, and that's it. So all of the drivers we wrote look like this. Couple lines of code, bang, you're done. I always like to joke that I'm lazy like a fox. I don't want to be typing and writing all this code all the time. I want to get my job done. And so we want to enable developers like you to be able to get things done quickly. And if we find bugs in these drivers, we fix them, and then you can just update. You don't have to rework your code or anything like that. So that's really cool, and one of the things I really like about what we did here is that it makes development for these kind of things really easy, because the IoT ecosystem, there's lots of these little devices, but they're really hard to talk to sometimes. We make that easy for you. So that's a quick little summary of the Android Things ecosystem. And so, as we said before, Android Things is based on all the tools that you're familiar with. Android Studio, the SDK, NDK, all the libraries and things like that. So it takes advantage of everything that you know, plus the power of Android and Google Play services and other things to help you build applications quickly and easily that work on IoT devices. Next, we provide software that's managed by Google. So the firmware images on the device, we push directly to the device and we build the images, and they're tested and they have security updates included. Android has a huge security team who spends time looking for exploits, fixing them, patching them, and so forth. You get all the benefits of having a huge security team like that working for you when you make an IoT device. And that's a real big win for IoT developers. You don't need to spend so much time worrying about new exploits in kernels and security libraries and things like that. And we provide BSPs and board support packages to make it easy to take those SOMs that we talked about and then build your own custom hardware that's easy to deploy and manufacture in different quantities at a price that's affordable to small companies and developers. So you don't need to be a billion-dollar company anymore to be able to make IoT devices. So we're really trying to democratize development here. And furthermore, at the end, we have automatic updates and an ecosystem around getting these things out to consumers. So you have the ability to make updates. We update different things as well. And we have that A/B updating mechanism that helps to ensure that if there's a problem, the device falls back. And it helps to, we're trying to make the IoT ecosystem more robust here. So with that in mind, how do you get started with Android Things? Well, it's really easy. So firstly, some of you might already have a Raspberry Pi laying around at home. So if you have a Raspberry Pi 3, you can just flash an SD card image from our website and put it in there, and it boots up Android Things. You can also use Intel Edison boards, which have been around for a while. They work with Android Things. We have devices from NXP who have a really sort of nice SOM design that's quite small. NXP is selling their boards as well. So you can choose the different kind of board that's appropriate for what you're trying to do. Some support displays, some don't. They each have different things that they're better at supporting. So you can go buy one of those and then you can try it out. We have a bunch of great samples that you can use that show how to do things like blinking lights and reading switches and how to do a weather station and things like that. And we also have a great Android Things community as well. So we have a G+ community that I run called the Google's IoT Developer Community, g.co IoT Dev. And that's where you can go to ask questions about Android Things, or if you have suggestions or problems, we discuss things like that there. We also have a community on Stack Overflow where we answer questions too. So, as I mentioned at the start of my talk, my job as a developer advocate is to come to events to talk and to teach about new products, but it's also our job to listen. And so I really want to talk to you and come up to me during the conference or during the lunch break or whatever, and we want to learn more about what you're trying to build with IoT and what things we can do to better enable that for you, and what cool ideas you're going to build. Because the thing with IoT is it's still a very new area, and we've got some simple little devices floating around, but the true killer apps for IoT have not been created yet. And I see all these people in the room here, and it could be one of you that creates the next amazing thing that everyone in the whole world wants to buy, and hopefully it'll be based on Android things. So with that in mind, thank you very much, and I look forward to talking to you at this conference. Thank you. So I was told we have a few minutes for questions before the next talk. So if anyone has a question, I'll be happy to answer it. I think we have people running around with microphones. I guess while we're waiting for the questions, make sure you follow me on Google Plus and Twitter as well, if you're interested in keeping up to date with what's going on with IoT and the Google Assistant. So I work on Android things, but I also work with Actions on Google as well. So if anyone has any questions about Assistant or Actions on Google, I can also answer those questions as well. All right, so we have a question somewhere?
All right, thank you for the talk. It was great. So I was wondering, can we expect to see Android things on devices other than ARM? ARM architecture. So is it going to be on other architectures as well?
Okay, so the question was, is Android things going to work on other architectures apart from ARM? Well, actually, the Edison boards are already x86 already. So the Intel Edison devices run x86. So when we made our TensorFlow libraries, we supported x86 and ARM right out of the box. So we're already supporting multiple platforms, just like regular Android does too. So whatever platforms Android supports, Android things can support as well.
Okay. Can we expect to see it in a lighter version, perhaps on some lower-end MCUs? All
right, so the thing with certain low-end microcontrollers is some of them can't be supported on Android things. So, for example, ARM v6, which is an older architecture, Android itself doesn't support those architectures anymore. There's various reasons for it, but the hardware doesn't support certain functionality that's needed by the code these days. So we don't support things like the Raspberry Pi W that just came out. That one was on an ARM v6 architecture. So there are certain low-end devices that won't support it. The thing is that if you're running a really low-end microcontroller, it probably doesn't have the memory and the performance to be able to support what we're doing with Android things. If you want to do really small real-time processing where you're reading a pin really quickly or doing something, in some cases you'll need to use a microcontroller because that's the right thing you should be using for the job. Because Android things is a Linux device or whatever, it's not a real-time device, so there's certain things you can't do. Like you can't fly an airplane with it because it's not able to react quickly enough to move the ailerons or whatever. So you've got to pick the right hardware for it. So it requires a certain level of processing, but the really cool thing is that it's good for vision processing, audio processing, really high-end things that have not been possible on microcontrollers up until now. Like I've been playing with some audio processing things, and you can't do it on a 5 megahertz device doing like a Fourier transform on some audio. It's just too difficult. So there's a lot of cool things that are enabled by this, but we're not going into the super low end.
Thank you.
Thank you.
Hi. Question, can you tell a bit about the deployment of your own app? So if you can, I imagine you can put it into an image that you then install on your device. And how does it get updated? Do you have to do it yourself, or do you also have a framework in place to update the user apps?
Sure. So you're asking about the update mechanism. So the Raspberry Pi mechanism is kind of unique because it comes in on an SD card. But the NXP device that I showed earlier is more of a normal Android device in that it has a USB connector on it, and you use ADB to push updates to it. And you update it with fastboot in the same way that you update an Android phone. But then once you've fast booted the firmware image onto it, it then gets updates from the network afterwards. So in the same way with your phone, it's flashed at the factory, but it also gets OTA updates later on via the network. So Android things works in exactly the same way. Raspberry Pi is unique in that it has an SD card that's removable. you probably wouldn't use a device like that to make a commercial product because your customers would pull the SD card out and mess around with it. But for most devices, the image is stored on the SOM and you update it with fast boot. And then once you've done that, then it gets updates via the network.
Okay, so via Play Store then?
It's not the Play Store. So we're going to be talking more about this probably at Google I/O. We have a whole bunch of talks at Google I/O done by the engineering teams that are going to give more updates about how this is done yet. We haven't finalized the mechanism that I talked about it a little bit, but the exact documentation for how we're going to do the updates is still going to be coming soon. So at I/O, we're going to have a whole bunch of talks about things like how we do the updates and how that's going to work for a developer. But right now, we don't have more than what I've just told you.
Okay, thank you.
Okay, no worries.